idea. Oh, I'm supposed to have been waiting all this time.
Oh, that's okay. She just got here recently.
Oh,
Hi.
good.
Yeah.
So, hi.
I told her to film it for me.
Oh, okay. Good. So, I'm going to get my gear and stuff out of the car.
Okay, cool.
I'm just going to finish this text, and even though I'm an EMF consultant, I do use a cell phone and texting, but I use it wisely, and we'll talk about that.
Okay, cool.
Okay. All right. So I'll be right with you.
All right, cool. Do you know what I'm doing with this guy today?
You're testing all your house appliances for radiation, right?
Yeah.
And I'm gonna help you record while you guys talk about what house appliances have a lot of radiation.
What do you think has a lot of radiation?
The microwave, for sure. All kitchen appliances like that you plug into the wall has some type of radiation.
Okay. Oh, yeah. Yeah, I think I'm sensitive to the radio.
Do you?
Yeah. Because if I use my cell phone, I get like a tingling in my head.
Okay.
Yeah.
I hear that a lot from my clients.
Oh, really?
Yeah.
So it must be real.
Yes. Yeah. Well, yes, it is. These are the meters that we recommend for our students to use.
Okay.
This is a radio frequency meter, made in Germany. A Gigahertz Solutions HF59B, and this is a more sophisticated and advanced version of the HF35C that a lot of people use for smart meters that you see on YouTube. And this is the NFA 1000, which measures magnetic fields and electric fields.
Oh, okay.
And this measures radio frequency fields. So between these two meters, we measure 3 of the 4 EMFs.
Yeah. Is this a tri-field? Is that what they call it?
Okay, so the tri-field meter, is that what you mean?
Yeah.
The tri-field meter, that's the tri-field meter.
Oh.
So, and the reason why it's called a tri-field meter is because it measures 3 fields.
Oh, okay.
The same 3. Magnetic fields, radio frequency fields, and electric fields.
Oh. Oh, I was actually thinking of like tri-axis.
Well,
I think that's what
that's all right. So these are all triple axis meters.
triple axis. Oh, okay, yeah.
As opposed to
The one that I have, I think is just one axis.
this is a single axis meter.
Yeah.
Right. Do you have your meter?
Yeah, it's in my room.
You want to go get it?
Yeah, sure.
Okay.
Okay, hold on.
Oh, this is the ED78S. Yes, this measures. This is the Cornet ED78S, and this measures magnetic fields and radio frequency field. So first of all, let me start out by giving you ladies my card. So this is my card with my website on there. This is for you, Esther. The camera.
Thank you. Thanks.
Okay.
All right, thanks.
My name is Oram Miller, O-R-A-M-M-I-L-L-E-R. I'm a certified building biology environmental consultant and electromagnetic radiation specialist, or EMRS. And my certification as a BBEC and EMRS comes from the International Institute for Building Biology and Ecology, or the IBE, which is based in Clearwater, Florida, although our executive director is in Santa Fe, New Mexico. And this is the American branch of the building biology profession in Europe, which was founded 35 or 40 years ago. A German architect by the name of Helmut Zia brought this knowledge from Germany to the United States maybe 27 or 28 years ago, and he founded the Institute for Building Biology and Ecology in the U.S. about that time. We just celebrated our 25th anniversary 4 years ago, 3 years ago, 2012, so 4 years ago now, in Washington, D.C. at a conference, and I was the chairman of the planning committee for that, and we had a nice video that we put together, a documentary of Helmut's life, and presented it to him, and he was there with his wife. He had had a stroke a few years earlier, which is why he stepped down as executive director, and Michael Kahn is our current executive director. So then Helmut died 4 months later. That was in October of 2012, and he died in January of 2013 from complications of the stroke. So we miss him dearly, and he's really the inspiration for many of us, almost all of us, to come on board. But then we've carried the torch and continued the training, of course, and we continue to grow. So I'm now part of the faculty. I'm an assistant instructor for the EMF seminars, electromagnetic field seminars.
The one that you sent me an email about.
Yes. The beginning one is every August. And the advanced EMF seminar, which has the second part of that knowledge. I have the full training in mold, chemical outgassing, water intrusion, building materials, picking ones that don't outgas, building walls that don't allow mold to grow in them and that dry out within the 36 hours before mold grows when you have a water leak. All the electromagnetic field training, and I did all of that for many years when I was in Minneapolis, until I moved to California 7 years ago, in 2010, 6 years ago. Yeah, January 2010, so just over 6 years. I'm in my 7th year. And I just decided I didn't like mold, and I love EMFs, so this is all I do. And there are other people in Los Angeles who do water intrusion consultations and mold analysis and indoor air quality identification and mitigation. I don't do that anymore. I refer clients to those individuals for those needs. What I focus on is EMFs. So they refer to me, I refer to them, and I just focus on electromagnetic fields. And I have been busy all these years without advertising.
And how come you're interested in this subject?
I don't know. I love puzzles, I love figuring things out, I love helping people. So this gives me an opportunity to educate people about a body of knowledge that most people don't know about. And even within the EMF safety community, per se, there are some misunderstandings about which EMFs there are, which ones are important, which ones we don't really need to worry about. So every day I work with clients through my website. They find me through my website and word of mouth, through healthcare practitioners and building inspectors, and just from clients mentioning me to their friends and family. So I help people to understand what EMFs there are in a home. So when I sit down with a person, as we're going to do now, we go over what EMFs there are, where they come from, how they affect human health, and what we do about them. And then we go around the house and take readings to see what the EMF levels are in your house. So that's what we're going to do. Every home and every family is exposed to all of these EMFs to varying degrees. There's not a home that doesn't have them unless we design it that way. Now, this morning I was in Woodland Hills for the 5th or 6th time at a home that was purchased by a electrically and chemically sensitive lady who she and her husband bought the house, and then over the last year it's being remodeled so they can move in with all natural, non-toxic paints and flooring materials. We've replaced the wiring with the metal-clad wiring here as opposed to the plastic Romex wiring like this, because this doesn't allow electric fields to come into the rooms.
What kind of metal is that?
This happens to be aluminum, but it could be steel or aluminum. As long as it's grounded at one end and continuous, this covering or sheathing or metal cladding holds in the electric field that comes from the hot conductor here, the black wire. Whereas the electric field from this will come right through the plastic, from the Romex. We call this R-O-M-E-X, Romex. It's a brand. Whereas this is called MC, or metal clad wiring. And this is flexible conduit, and we have the rigid conduit. So this is a rigid conduit, or EMT, or electromechanical tubing, right here. So these two are shielding of one type of EMF, the electric field, not magnetic fields, but the electric field.
Oh, okay. And this is also aluminum?
This is steel.
Oh, that's just steel.
Yeah, this will be steel. They don't use aluminum for this.
Oh.
They will use aluminum for this, or steel. Either one is fine. This allows the electric field EMF to come out, because electric fields are the E of the EMF, and magnetic fields are the M of the EMF, the electromagnetic fields. There's both of them. Neither of these contain magnetic fields. The way you keep magnetic fields from coming into your living space is by making sure that the current load on each conductor, the hot going one way and the neutral coming back, are equal. And that the two wires are together. And if you satisfy those two conditions, there will be no magnetic field in either of these. Because if you had an unbalanced load, like if you just put the hot wire, the black wire in here, this would not contain the magnetic field that would produce. You must have a neutral with it, with the current going back the other way of equal amount. And then there will be no magnetic field from either of these. So we'll go over that, okay? All right, so at this point what I do is I go over with the clients what EMFs are and where they come from and how they affect health and what we do about them. Okay, those are the 4 things we do. So my website, which is www.createhealthyhomes.com, homes is plural. So we have version here. So this is this is what my website looks like. You always see this banner here, and you always see this menu on every page. No matter what link you go to, you see this. This is the page that you come to when you click down here on Building Biology Safe Exposure Guidelines. Because this lists the numbers that we strive for in a home for the different kinds of EMFs. If you're in the low levels, then you should not have symptoms from the EMFs. Now, before I show this to you, I do want to mention that we cannot predict or make any statements that what we do is going to change someone's symptoms if they have symptoms, even if they're convinced that their symptoms come from the EMFs. And how you know that is because when you're away from the home or when you turn off certain lights, then you feel better. Now, of course, if you're away from the home and you feel better and you come into the home and you feel worse, it could be many things. It could be mold, it could be outgassing from something, which you'd smell. You'd smell the mold, usually, not always. And, or if only initially when you walk in and within 5 minutes you don't smell it because you've habituated to it. So if you know that you have symptoms from EMFs, the degree that we can't make any claims that you'll have improvement in your symptoms from the work we do, because we don't know what other factors are involved. But what we can say for sure is, to the degree that your symptoms are caused by these fields, and to the degree that we are able to help you to reduce them, and assuming there are not other factors that are maintaining those symptoms, That's the degree of improvement you can expect. And that's what the majority, the vast majority and bulk of my clients tell me.
Yeah.
That they do feel better when we reduce these fields. So
That's
it's
good.
important to identify them. All right, so when you click on this link right here, Building Biology Safe Exposure Guidelines, this is what you see. But you don't see this anymore. This is the old 2008 version of the, because I actually put the guidelines right here on the page, and we have these tables with these different categories, which I'll explain. Now, just a few months ago, they came out with a 2015 update. The numbers are all the same, they just changed the wording from no concern, slight concern, severe and extreme, to anomaly. So I took this text off of here from 2008, and you still see this part, and then you see a link here that says, to see the latest version, click here. And when you do that, this is what you see. This is a PDF. It's from the German building biology profession, okay? Actually from one gentleman there. And they said, by all means, we can use their guidelines, because we're cousins, you know, sister organizations.
What is an anomaly?
Anomaly just means
That it's out of
problem, or, so in other words, so we have 4 columns here. And this is for sleeping areas. If the readings we get with my meters and your meter are in this column, then we consider it to be no problem, no concerns, the old word, no anomaly. For people, for healthy people in their bed, wherever they sleep. Slight anomaly would be this group of numbers. Severe anomaly would be this group of numbers, and extreme anomaly would be this group of numbers. So we try to get our clients, our goal is to get our clients out of these 2 columns, severe and extreme, and into no or slight for healthy people. If you're extremely electrically sensitive, then we try and shift you even into the no anomaly level, which is not easy, to do. It's just really hard to do in an urban environment. But we'll see. So that means that this is our guideline here, or our between slight and severe, right here. So for magnetic fields, and we measure in milligauss here in America, mg, not nanotesla like they do in Europe, we try and get people below 1 milligauss. For electric fields, using the field strength meter, which is this one right here, we try to get people below 1.5 volts per meter. Or if we use the body voltage method, below 100 millivolts. We say more than 10 volts per meter is an extreme anomaly, or more than 1,000 millivolts, using the body voltage method, is an extreme anomaly. But you can have that. It's not healthy, but... And if you're more than 5 milligauss, then you're in the extreme range. And I had a client yesterday in Irvine, in Orange County. For 17 years, she slept in a field, at least during the day, with loads on in the house. It was 8 milligauss. That's probably lower, as she has tenants in the bedrooms there, turn things off. But some of them stay up pretty late. And so I asked her to check that with her Gauss meter last night, because she moved to the end of the bed, because she got a meter similar to this, called a cell sensor, and she was able to see how high the magnetic field was. So she moved, and she didn't know what it was, so I determined it was a wiring error, or multiple wiring errors, or wiring errors on multiple circuits. So I'm returning on Friday with an electrician who's gone through this training, who I work with, one of 2 gentlemen that I work with, and we're going to go fix those wiring errors on Friday. So,
that's good.
Yeah.
This one, it measures it in milliwatts per meter squared, and also in volts too.
Yes, that's radio frequencies.
Oh, yeah.
But then in the LF...
This is for Gauss. It measures in Gauss for the low frequency.
Yes, but...
or milligauss. Wait, let me see. Microtesla.
Well, microtesla, but down here is milligauss.
Milligauss, yeah.
Now, Jerry Day is a smart meter activist here in Southern California, and he and I know each other. Almost 2 years ago, he emailed me and said, could I recommend to him a set of inexpensive meters for viewers of his website to buy and then take their own readings. And so this is...
That's one that you recommend?
I did. And so his website is, he has many, but one of them is EMF Help Center. So he's also documentary filmmaker.
Yeah.
And he has a camera.
Oh, cool.
Like
Did he
us.
make a documentary?
No.
Oh.
But we spent 2 days in Altadena at a friend of his house, an architect up there, and we filmed the content of the videos that are on his website, emfhelpcenter.com, where he sells these.
Yeah.
And you know.
I got mine from stopsmartmeters.org.
Right, that's another excellent organization. They're up in Northern California. So Jerry sells these meters, and he gets, you know, the profit that he makes from getting them wholesale versus selling them retail, the same price as everybody else, helps him out financially. I don't get anything for it, but underneath each of these meters, we have a link to a video that he filmed with me explaining what the EMFs were that we're trying to measure with each device. And this company has come out with a new model called the ED88T instead of 78S. It's 88T, which has electric field detection and a few other changes that are improvements.
So it's electric and magnetic.
And radio.
And radio.
All three.
Yeah.
Yes. And actually for $189 for that one and $139 for this, it's pretty accurate.
Yeah.
I mean, these are $2,000 each. And you know, they're not too off.
Wow.
This one compared to these guys.
Yeah.
Actually. So
That's pretty cool.
I mean, these can data log and peak hold, and actually that has peak hold.
Yeah.
And you can't data log with this, but you see the histogram on the right.
Yeah.
You know, so this has a lot of features, which are it's kind of nice.
But is it a one axis or is it?
No, that's a single axis meter for everything it measures. So you must hold it in the different orientations.
Yeah, that's what I
to make sure you don't miss the field. So magnetic fields are the first type of EMF, the M of the EMF from house wiring.
Yeah.
The electric fields from house wiring is the second type of EMF, and they're separate from each other for reasons I'll explain in a minute. Then all the wireless radio frequency fields are the third group, and they are EMFs as well. They're just faster frequencies. And then dirty electricity, again, is another type of EMF because it has an electric field and a magnetic field component, as do the radio frequency.
Is the radio frequency consistent of electric and magnetic field?
There's an electric field component and a magnetic field component to all of these.
Oh, okay.
So even dirty electricity has an electric field component and a magnetic field component. You notice I'm doing this because they're at right angles to each other.
Oh, yeah.
In space. It's just what frequency are they? So house wiring is 60 cycles per second. Dirty electricity is 2,000 to 100,000 cycles per second that we generally see. And then the radio frequencies are at 800 million, 900 million, 2400 million, 5 million, 50, 100 million, no, 5,000 million, or 5 billion. So 800 million cycles per second is 800 megahertz. 1 hertz is one sine wave, one cycle, positive, negative. So 800 of those, 800 million of those is 800 megahertz, because one cycle is 1 hertz. So 800 megahertz, 900 megahertz are typical cell phone frequencies, 1800, 1900. And then 2400 megahertz is 2.4 gigahertz, which is the frequency of Wi-Fi, as well as 5.8 gigahertz.
Oh, yeah.
Okay, so it's all in that section. So, okay, so the way you use this chart is you look at the type of EMF, and we're going to use this all afternoon today, and then we see the number that we get with our meters, where does it fall on this spectrum here? Which category are you in? So we want to get our clients into these two categories, the no anomaly or slight anomaly categories for sleeping areas, and then for the daytime we extrapolate from there.
Yeah.
You have a little wiggle room for some of these things, not magnetic fields, but electric fields we're all exposed to levels up in this range, and most healthy people can handle that.
Yeah.
There are a few situations where we don't want to have electric fields in the daytime, like ungrounded laptops or computers and an ungrounded outlet for your refrigerator. where you have, so instead of having an outlet that allows the ground to go in, because the plug for modern refrigerators has this.
Yeah.
But if the outlet is only two-prong, then what people do is they put in one of these things, this 3 to 2 adapter.
Oh yeah.
So that goes into the wall, and then your refrigerator goes into that. But where's the ground? It's not connected.
Yeah.
And even if it was, under the screw of the cover plate, half the time there's just 2 plastic wires back there, or cloth wrapped for that matter, with no ground. So it's an ungrounded refrigerator.
Yeah.
And you end up with very high electric fields in the kitchen. And it's not healthy.
Yeah.
Now you can also have a laptop with a cord that has this kind of a plug on it with no ground. And when you put your hands on that laptop, you have exceedingly high electric fields, which drains your energy. And you wonder, why am I tired when I sit at my computer for more than 20 minutes, let alone for hours, like some people do. Okay? What you want is you want this. You want the plug to have this. Or, if not, you can get a replacement power cord that has this on it from prontocharger.com. Or you can get this from Less EMF. LessEMF.com.
Yeah, I have used them before.
Okay, in upstate New York. And this is a plug to USB patch cord. So it's called a USB ground cord. This is the neutral. I believe that's right. But these 2 blades are dummy blades. They're just for stability. They don't attach to anything. There's only one wire coming out of this, which is attached to the ground. So you plug that in, and this goes into a USB port on your computer, and this grounds the chassis of your computer.
Oh,
so this is like $9 from LessEMF.com.
Oh, okay. I've never seen that before.
Yep. So these are the kinds of mitigation steps that we do.
Yeah.
You know, so with a computer, you can have magnetic fields from the computer, electric fields, radio frequencies, and dirty electricity. And I have a page on my website, Safer Use of Computers, which breaks that topic down, identification and mitigation, by type of EMF.
Yeah.
But with Apple, you can't unplug this. It goes right into the computer.
Oh, you can't?
No, it just disappears into the back of the computer. You can't pull it out. Now with a laptop, you do have a low voltage cord, because a laptop and a desktop for that matter, all the components, the circuit boards, operate at 9 volts, 6 volts, 3 volts, 12 volts. There's multiple voltages in there, so you need a switch mode power supply for each one, and that creates some dirty electricity, but it's another topic. But the block, has 120 volts coming into it, and then it's a step-down transformer from 120 volts here in America to 19. They almost always say 19, because you can see input 120 volts AC, output 19V DC. So it has a rectifier to convert AC to DC, and it steps down, and there's a magnetic field that comes out, but only about that far.
It comes out from the block.
Because it's a transformer. It's a point source of magnetic fields. And then 19 volts goes down, but with Macs, you can slide that cord off and put an adapter on there with 2 little blades that swing out, and then you put the whole white thing down into a surge protector or into the wall.
Oh yeah, I need to find mine.
But it's only 2-pronged.
Yeah.
There's no ground on that thing.
Is that bad?
Yes.
Oh, okay.
Because then that renders the whole laptop ungrounded.
Yeah.
So if you pull that off and put the cord back on, which has this at the end of it, then you've restored the grounding of the whole thing.
Yeah. That's the one I use.
Good. So if you use that, then you're good. Now with clients who don't, I ask them to find it, and half of them say, "Oh,"
I can't find it.
And then they always do. They always find it. Batting 1,000 on that. And I can show them what the electric field levels are to start with, and then what they go down to, and then they won't have that fatigue.
Yeah.
And by the way, Apple, according to a client told me that Apple is going to I think the current model years forward, or very soon, from now on, you can't take that cord off. It's going to be hardwired in.
So that's good, right?
Good for us. They're not doing it for health reasons, I don't think. I would be surprised. And he told me why, and there's a technical reason why, which makes sense.
Yeah.
So whatever reason they
Yeah.
chose, we're happy about it because it means all the new ones that are coming out that people buy will not have that problem
Yeah.
anymore of high electric fields because it's important to us.
Yeah.
And you don't get rid of high electric fields with your laptop, whether it's a PC or a Mac, with an ungrounded two-prong plug by putting your foot on an earthing mat. There is a video going around where a gentleman shows people with a body voltage meter, and he says,
Yeah.
look how high this is, folks. When I look on the meter, when I put, he's holding onto a probe going to the meter, which I have in here and I can put together for us.
Yeah.
And he puts this other hand on the laptop and he says, well, here, watch that number go down when he puts his foot on an earthing mat.
And it does.
But he's looping, he's running that current through his body, and that's not a good thing. We don't agree with that. We ground the computer, not the person. So by grounding the computer, you don't have that in the first place, and we don't want it running through the person, and because then you're in that test. This belies the real problem because it gives you a false sense that you're protected, because the only reason why that number goes down is because you're doubly grounded. You're grounded with the probe and you're grounded on the so of course that number's going to go down. I can demonstrate that later.
Yeah, that makes sense.
So that's not the solution. The solution is to get one of these and ground the computer.
Yeah.
Well, that's what we recommend.
Oh,
okay.
The battery is about to die.
Oh, I have another battery.
Okay, it's just 38 minutes. I just want to say.
Okay.
Oh, okay.
So let's go over some of this stuff. Now, so when you have your other battery, how much time do you have with that? Do you have any idea?
No.
How long do you think it
it's
lasts?
supposed to be an hour. It's sometimes not this long.
This was like 78 minutes.
That's what it says?
Yeah.
Can you charge this one up while we're using the other one?
Yeah.
Because I have more than an hour's worth of stuff.
I know.
And we haven't.
I also have other she has a camera too.
Oh, okay.
Yeah.
All right. So for electric fields, we want to get below 1.5 volts per meter or 100 millivolts. For magnetic fields, we want to be below 1 milligauss. And ideally for radio frequencies, for sleeping areas, we want to be below 10 or so microwatts per meter squared.
Mm-hmm.
So those are our goals. And for dirty electricity, we want to be below 50 to 100 units on this meter here.
Yeah.
So you'll see that when we plug it in. Okay. So
I read the book Dirty Electricity.
by Dr. Miller.
Yeah.
Yes. And we've met him. He comes down to Palm Springs area every winter from Washington State.
Yeah.
Good man.
Yeah.
So for EMFs, when electricity was first deployed in Brooklyn, New York, it was all one polarity all the time because it was direct current, and this is Thomas Edison.
It was like this, right?
Well, no, it didn't go like this. It went like this. If this is distance, it was always the same polarity and the same strength, 120 volts. But it was DC. It was like a battery. It was direct current.
If it's DC though, I thought it just goes like that.
No, it just stays right here.
Oh.
With time and if this is time or distance, it'll just be the same voltage.
So
actually,
there's
no oscillation.
Up and down.
No, that came about from Tesla.
Oh.
I'll get to that. So it's just that if this is distance, then the voltage steadily dropped the further away you got from the power plant.
Mm-hmm.
So in Brooklyn, in 1905 or whenever, the turn of the last century, they had to have little coal-fired power plants every few blocks to produce electricity.
Mm-hmm.
But the street lights were dimmer 2 blocks away than they were right next to it. And if you lived 2 blocks away, your lights were dimmer than your friend who lived right next to them.
Yeah.
So Tesla said to Edison, in order to have electricity go for miles, let's alternate the polarity in a sine wave fashion.
Yeah.
You go from 0 to 60 volts to 0 to 60 volts to 0.
Yeah.
And so 60 volts up, 60 volts down, that's 120 volts peak to peak. And in Europe, it's 240.
Yeah.
Goes up twice as high and twice as low, and it's a little bit fewer per minute per second, because they have 50 cycles per second, we have 60. So we pack 10 more in per second.
Is that worse for?
No, they're both, you'll see in a minute.
Oh.
So just so you understand, one cycle is comprised of two halves, a positive half and a negative half. But it's so 60 times a second is fast enough that to a light bulb or a motor, it looks like a steady 120 volts all the time.
Mm-hmm.
And so they could project it down the wires for miles.
Mm-hmm.
Okay, so that's how they got around that. But it's not good for people.
Is DC better for you?
Yes. I know some electrically sensitive people who have rewired their house to run on 12 volt or 24 volt DC, like houseboats do and RVs and campers and such. You can get lamps and refrigerators that run off DC.
Yeah.
And then they have one or two sockets for AC, which is funny because the computer is low voltage DC, but you got to go through AC to get there because.
And why do we still have AC? Just so that everything goes faster from the power plant or something?
Well, because remember, DC does not allow the electricity to go very far from the power plant.
Yeah.
AC has allowed us to develop centralized power plants that send the electricity for miles.
But like say somebody has solar power, that would be DC. They could avoid using AC if they wanted to.
Yeah, but all right, you're right. And in Germany, a third of the houses, through government subsidies, have solar panels. With all the clouds they have over there, that's what they've done.
Yeah.
A third of the houses, and that's probably expanding. So it's just that you need to convert it to 240 volts over there in Europe. And then from there you have to step it back down again because all these things that run on DC are at different voltages. So every transformer is different.
Yeah.
You can't swap them out. They have different voltages and also different polarities for the tip and the ring.
Oh, so that's why it's easier to go through AC.
Well, but everything's standardized. Everything is built to 120 volts in the US and Canada, in the Western.
Yeah.
Well, we're all the Western Hemisphere, but all the Americas are 120 volts. Europe and Africa and Asia are, Australia, they're 240. I don't know about Australia, but those are all 240 volts. So, but they're all AC. Nobody's gone back to DC because it would die out within 2 blocks.
Yeah.
Does that make sense? Does that answer your question?
Yeah, well, no, I was just saying, like, for, like, one house, you know, the house could get by if they use solar power, but...
Oh, that's right. So the problem is the solar power comes down at 24 volts, but your laptop is 19. Your clock may be 3. I mean, how are you going to...
So you need something to make it universal.
Well, but see, the appliances are all different.
Yeah.
So they have these transformers which start from 120 volts AC and convert it to all the different voltages that all these appliances have. Now, if every house had 12 volts or 24 volts DC, then you'd still need transformers because not everything runs on 24 volts.
Yeah.
You have a lot of circuit boards, that's too much.
Yeah.
They still need to go lower.
Yeah.
But that's what comes off the solar panels. So you'd need a transformer. See?
But if it was transformer from DC to like a lower voltage DC,
well, you could do that.
That would be better, right? Because it wouldn't be dirty electricity.
Yeah, okay, so you're not thinking of a community, you're thinking of just one house.
Yeah.
Now, there are people who do that, but the
Yeah.
problem they run into is who makes, you know, you still have to, I don't know that anybody makes, I guess they do, but a transformer that goes from 24 volts to 3 volts, or 24 volts to 19 volts. Because let's say they want to run their computer. If and engineers do this, they'll come up with a transformer that takes whatever comes off of the solar panels and converts it to what needs to go into the computer, which is 19 volts DC. So they can do that.
Yeah.
Now, there may be some more modifications that have to be made. But the technology isn't there to convert from 24 volts DC to all the things that people use. But the technology is there to go from 120 volts AC for all these devices.
Yeah.
It has to. If you're going to make a clock or whatever, it has to work off 120 volts AC.
Yeah.
So if there was enough demand for 24 volts DC, they would do that, and maybe that does exist. I've never been asked that before. That's a good question. Actually, the issue has come up now that I think about it, and that's the obstacle we keep hitting.
Yeah.
You can't go to Walmart or Amazon and buy a computer that works off of 24 volts. They all work off 120 volts AC. See the problem?
Yeah.
So, oh, okay.
So 24 volts, that means it's DC, or what does that mean?
No, the voltage is one thing, and then whether it's AC or DC is another thing.
Oh, okay.
Because again, alternating current means you alternate the polarity from positive to negative, whereas DC is just the same voltage all the time.
Yeah.
Like a battery is just 9 volts DC.
Yeah.
It always comes out one end and always goes back in the other. Or in your car, it's all DC, 24 volts DC.
Yeah.
So, or 12 volts DC in the car. I think that's right. But we're trained in houses. I know house wiring very well. I don't know cars that well.
Yeah.
So now the thing about this is, this sine wave we has, when electricity flows through a wire or comes out of flows into a transformer or motor, we have fields. We have an electric field component and a magnetic field component. We have an electric field component vertically and a magnetic field component horizontally. They are at right angles to each other.
Yeah.
So this is what I meant when I did this earlier.
Yeah.
Now, the question is, do you have both all the time? Or can these be different?
They
And
could
the
be
answer,
different.
well, it depends on the frequency. Because in the near field, they're independent of each other. The near field is defined as within 3 wavelengths. Now, this is the wavelength from here to here, because there's actual, even though these are invisible, like this room is filled with waves that we cannot see, because our eyes can only see a certain, well, here's the wavelength that our eyes can see, right here to here. This is wavelength on the electromagnetic spectrum.
Yeah.
This is the spectrum here in cycles per second, which is frequency, or hertz. 1 cycle per second is 1 hertz. H-E-R-T-Z is a man's name. And they abbreviate it as capital H, small z.
Yeah.
And then the wavelength is in meters. And as the number of cycles per second gets faster, and that frequency gets stronger, or a higher number, the wavelength gets shorter. So the two numbers are inversely related relative to, as this goes up, this goes down. So the wavelength gets shorter because you have to pack more of them in per second. Now, beyond 3 wavelengths, they're coupled. So if one goes up, the other goes up. If you measure one, you can calculate the other because they're synchronous. They're coupled. And that starts, okay, so they chose 60 cycles per second for AC electricity in America. The wavelength for 1 cycle is 3,100 miles. And so the far field is 3 times that, which is 9,000 miles. So you're never in the far field. So you're always in the near field with house wiring. So you always have the situation where you can have an electric field and no magnetic field. You could have a magnetic field and no electric field. Or a little bit of one and a lot of the other, or neither. They're independent of each other. The reason I bring this up is because a lot of people will go around with a tri-field meter and they'll turn it on and they'll get that, which is next to nothing for magnetic fields, and then they'll switch it to electric fields and they also get next to nothing.
Oh, you're on radio.
Sorry.
Yeah.
See? Now, the problem with this meter is it's not sensitive enough as far as we're concerned in the electric or radio frequency settings. That's just based on these numbers.
Yeah.
This meter is not capable of going low enough to measure these. Because you could be up into the extreme level and still be close to zero on this meter. So, whereas this is more sensitive and for radio frequencies, and the new one for electric fields than the tri-field meter, with all due respect to the Alpha Labs who designed this. Now, and it turns out that with the frequency weighted model, which is the one that, this is a frequency weighted model, there's some distortion of the reading at higher harmonic frequencies, like dirty electricity, where it's 2 to 4 times, it gives you a number that's 2 to 4 times higher than the number actually is. And that's part of the design of an analog meter, as opposed to a digital meter, which is what this is. This is a digital meter.
Yeah.
So, there's an issue of accuracy. So this tends to overstate the case, because this will be at 8, and my meter will be at 1.2.
Yeah.
And people are saying, but the guidelines say be below 1, and my meter says 8, or their meter says 8, but my meter says 1.2. I said, I'm not so concerned about this. What they're picking up is dirty electricity in the air, which a lot of people who look at the internet think is the worst thing, and in fact, we think,
it's not
wait for this, it's, as far as we're concerned, it's number 4 on the totem pole. It's not as bad for healthy people as the other 3. But nobody knows about, I mean, everyone knows about radio frequencies. Nobody knows about these 2. Electric fields, nobody knows about that. And magnetic fields, everyone's heard of it, but nobody pays much attention to it, and they don't know how to fix it. So we have the knowledge of how to fix magnetic fields from wiring errors and current on water pipes. And electric fields, we know how to fix that too, and nobody knows about electric fields at all.
What do you mean nobody?
Nobody talks about it.
Like the health department or something?
No, I'm talking about, I'm sorry, good question. Well, yeah, that's true. But even within the EMF safety community, you don't hear any discussion of electric fields except a few. There was only a handful of people. Lloyd Burrell, a British man in France. He knows about this. I was on his show just 3 weeks ago. Jeremy Johnson knows about it. Sean Cranish in Illinois knows about it. Jeremy's from the Bay Area, but he happens to live in Europe as well. He has an EMF blog. So there are a few people. Stephen Scott, who's an electrical contractor who used to live in LA, well actually he still comes down here, but he lives up in the Bay Area. He knows about this. Also Michael Newart, who's in the Bay Area, he knows about this. None of those guys are building biologists, but they know about electric fields. But everybody else doesn't, unless I've left a few people off. But
so now I know about it.
Well, yes, and the point is, electric fields are the most common EMF there is. They're in every bedroom, and that's where we pay attention to them, is where you sleep. So I'll get into that, okay? All right, so now, so the problem is people will go into where they sleep and they'll turn on electric fields. And not only does this not show them, most people don't even think about it, especially if they have just a single Gauss meter without electric field, like the tri-field meter has. So just as an example.
And the Gauss meter is what, just the magnetic?
Yeah, Gauss means magnetic fields. Now this is a very sensitive, freestanding, ungrounded, I can ground it through a jack here, but it's an ungrounded, so I'm going to just set it here because you're not supposed to touch it. And okay, now the electric field levels at this location are actually relatively low anyway.
Really?
They're at 1.5.
Yeah.
Which is,
can you film that?
And 0.9. The problem is I can't get this thing to stand up.
Oh, there you go.
So it turns out that in this, sitting at this table,
it says 4.3.
It does say 4.3?
It's going up and down now, but it's like
well, it fluctuates. Now she's getting closer to it with her camera.
Yeah.
So
oh, is that why?
It could be.
Okay,
and as people get close to this thing, it will go up.
Yeah, it just went down.
And I don't know if my water bottle enhanced it. I don't know. But anyway, this thing is it fluctuates.
Going up and down. Yeah.
Okay. So.
But what's a higher, like, what's the normal electric field?
Well, in the daytime, when you're near this kind of wiring, this plastic wiring, it could be 600. That number could be 6, 8, 10, 15.
Yeah.
You know, remember 6. 10 is extreme. We want it to be below 1, which it is, which is good. Now, I have a feeling that this building may have this kind of wiring.
Really?
Just based on the era in which this was built.
Oh.
Maybe not. We'll find out.
What era is that?
60s, 70s.
So you think it was built in the 70s?
You know?
No, I don't know.
Yeah, judging by the look of it, I would say this is not a 40s building. This is more like 60s, 70s.
Oh, okay. I didn't know.
Yeah. So anyway.
Well, that would be good.
Yeah. Now we're going to move this to magnetic fields, and this is good. 0.3.
Oh, it is.
Anything less than 1.0 is good. This is 0.3.
Yeah.
Now we're on magnetic fields.
Yeah.
So that's a good number. Anything less than half a milligauss, which is 0.5, is really good.
It's probably better in my bedroom.
Yeah, we'll find out. Well, this is low enough.
It could be worse.
But Nicole, this is good enough.
Yeah.
You don't want it. I mean, it'd be ideal if it was this low.
In the
There.
bedroom.
Yeah, we'll find out. We'll find out.
But I have my computer on right now, so that would affect it.
No.
No.
Um, only this far from the transformer.
Oh, right.
So you'll see.
Okay, yeah.
Okay. So I told you that we have an electric field component and a magnetic field component here. And then so 60 cycles per second is right here.
Oh, is that your one?
Yeah. So 60 cycles per second is right here. So this is one area where we have EMFs.
Oh, extremely low.
Well,
Or
ELF means extremely low frequency. It just means less than 1,000. And then 1,000 to about 1 trillion is the radio frequency or RF band. AM radio is here in the kilohertz or hundreds of thousands of cycles per second. FM and TV are megahertz. KCRW is 89.9 megahertz or millions of cycles per second. Your cordless telephone is 2.4 gigahertz.
So the higher up the frequency is, the worse it could be. Or?
That's one parameter. Digital versus analog. Digital's worse. Also, but also the power, mostly the power density, because you can have a given frequency, two signals at a given frequency. This one's 1 watt. This one's 1,000 watts. Your cell phone is a half a watt to 1 watt of energy that it puts out. The cell tower broadcasts at 800 to 1,000 watts.
So
and
that's worse.
Yes, and then what's an FM radio station? 50,000 watts? 25,000 watts, you know, so it just depends on how many watts. So, but they're on Mount Wilson.
Yeah,
The FM.
so they're far away.
Yeah, they're farther away.
So
when you,
it's harmful.
now the receiver is not a problem for most people.
For the radio.
Yeah. But the cell phones are transmitters
They're also
and receivers. So
Yeah.
the harm comes in the transmission.
Oh, okay.
All right, so there are health effects for these things.
Also, I have radio microphones because I'm a sound mixer. So with my,
wireless.
I've tested it with this with my receiver, and
Okay.
it still picks it up from the receiver.
Yes, right.
Receiving end.
Do you know if this causes like learning disabilities?
Yes, you can.
So does autism? Do you believe it could cause it?
Yes. There's a whole group of people in San Francisco who believe that.